All right, hello everybody. This lesson is the actual sine, cosine, and tangent ratios, or the buttons you see on your calculator, sine, cos, and tan. Big acronym, made-up word we're going to use to help remember to SOHCAHTOA. There's the bottom of that. So in the previous lesson, we looked at this basically the fundamental tangent ratio. We saw this yesterday as really the rise over run ratio, and so we'll see that again as part of this class. So the main things to know for labeling sides correctly on triangles is be able to point out or pinpoint which part of the side on the triangle is the opposite side, the adjacent side, and the hypotenuse. So I might just use OPP, ADJ, and HYP for short here. So, I find it's obviously really easy to identify hypotenuse. Wasn't what I was going to start with, to be honest, but the hypotenuse we've already done. Right, so we really should be able to point out across from the 90-degree hypotenuse, across from the 90-degree hypotenuse, across from the 90-degree hypotenuse in each of these triangles. And so that's going to be down here as well for the other set where we're looking at the other angle, but this is still obviously the hypotenuse, hypotenuse, and hypotenuse. And I'm not going to leave it here, but across from 90 degrees or shows, right? But I don't have that because it'll get in the way of the other area I want to show. So on the opposite side of the triangle, it's a very physical thing. I always tell my classes that I like to teach in a triangular classroom at some point, a right angle triangular classroom. So I'd be able to have students in this corner, right in here, right where the X is, and definitely point to the opposite side of the classroom. Clearly, that's the opposite side of the classroom over there, right? These two walls here and here are the ones that are kind of beside the X angle, right? The X corner. So same thing over here, opposite over here, opposite here, right? But really, I just going to label the opposite on the first one. Maybe I'll erase those for now. Right? I don't know. I feel like maybe I'll just put them all in, but so the reason I feel maybe you should have them all in is because when you're trying to identify the adjacent side, the hypotenuse kind of needs to be labeled, because if you're standing in this corner of a room, then the sides that are beside you or adjacent to you is the English language word that actually exists, but is used a whole lot. The side that's beside you are these two here, this one and this one, right? But obviously the longest side across from 90 degrees already labeled as the hypotenuse, and so therefore this one must be the other one, the adjacent side, right? And so you kind of need to have the hypotenuse locked in to make it obvious which one's the adjacent side. So obviously all three sides can be filled in. And right here for the Y angle, then the opposite side now is this one. So the opposite side of the room from the other one, right? And then the adjacent side, well, which side is adjacent right beside the angle Y? Well, the hypotenuse is this one, so this one must be your adjacent. And of course, the hypotenuse are being labeled everywhere, right? So in the end, change the file here, maybe a little different organization, but this is the three sides all labeled here relative to angle. Key thing here being relative to angle Y, at the opposite, the adjacent, and so on. And then the same thing on this one, the opposite, the adjacent, all labeled there. Okay, so you got to practice, you got to get good at just labeling which one's which, because that's going to be necessary for the trig ratios we're going to be doing. All right. So obviously here you try on any of these slides yourself. It's pretty easy to do. So you can anchor in the hypotenuse right across from the 90 degrees. So you get this sort of bicolored word there for hypotenuse. That's the opposite side regardless. And we can say, okay, well, the opposite side of the triangle from this would be over here, and the adjacent side must be this one, because these two here and here are beside it, but this one's actually the hypotenuse, so the other one's the adjacent, and so on and so on. Same deal for the groups, right? Gets a little confusing if you label both, but this is the opposite side over here to the green angle Y, and it's the adjacent side to the angle X. First. right? So there's another one there still in practice. It's the same stuff over and over again. So the slope ratio that we've already seen is that opposite over adjacent. That's officially the tangent ratio. But just want to remind you what we saw to do with that. We had tan of 31. We did tan of 40 degrees before. Tan of 31 degrees. If I grab my calculator, make sure my calculator's in degrees mode. Tan of 31 gives me 0.60 or so. And that is equal to this rise over run number, right? It's equal to the opposite over the adjacent we're going to see in the next slide, but it's equal to the rise over the run for now at least. So tan 31 equals 0.6. And that's going to be the same regardless of what version of this triangle we see. You'll see bigger or smaller versions. So one that's half the size, it's going to be a 3/5 ratio. And of course, the tan button is still going to give the 0.6, but the 3/5 and the 6/10 both agree with that value. They both give that 0.6. 0 number. Right? And then down here, if that numbers that weren't as obvious, tan of 31, obviously it's still going to give us the 0.60. And in this case, it must be equal to the 4.5 over the 7.5. If I calculated things right, so 4.5 by 7.5 gives us 0.60 again. Yeah, so basically what I'm connecting to is what we've seen before of the tangent ratio being really like the slope ratio from this. Okay, so any angle, any triangle, right triangle with an angle of 31 degrees is going to have this same slope value, meaning like 31 degrees dictates your slope, right? So slope equals 0.60. Well, it's also equal to the tangent number, right? Tangent of the angle. And tangent just needs a particular ratio of sides, rise per run in this case. So that was just a nice way to introduce the topic, help you see what the buttons really do. They really just give you a ratio of sides. Now we're going to show you the rest of the story. So the three primary trig ratios, the tan one we already just talked about, opposite over adjacent, check, rise over run, basically. We need to look at the opposite over hypotenuse for sine and adjacent over hypotenuse for cos. And the way people like to remember that is to say SOHCAHTOA. And so the sine ratio, right, we're looking at the opposite side over the hypotenuse. And the cosine ratio, we're looking at the adjacent over the hypotenuse. And for the tan ratio, we're looking at the opposite over the adjacent. Okay. Yeah, so just that's going to need to be known, and then we'll show the uses of it. Okay. So today we're going to look at solving for sides, and then we'll do solving for angles. Just to make it an easy start to the year, an easy review. So some of the skills you need to do, of course, you need to be able to do sine and cos and tan now of different angles. So for example, this is literally just figure out how to use your calculator to do sine of 40. Some calculators hit the sine button and then 40. Some calculators hit the 40 button and then do sine of it. Okay, whether your calculators direct algebra logic or the other order. So 6/4 ... tan of 50. I'll just run these numbers so you know if you're doing calculator work right. One ... and cos of 35. 0.819. So 0.81. I'll do the 9 and then ... just to make not be as misleading about, so you know you got the right number. So that's just evaluating. So in this case here, you could picture the sine 40, right, being the opposite side over the hypotenuse, whatever these numbers are, right? Those numbers would give you a value of 0.64, and each one of these has an equivalent ratio logic. We did the tan of the 50 degrees. Let's go a little bigger angle, make that be a 50. Then in this case, the opposite over the adjacent. That's what tan is. So we'd be saying tan of 50 equals, this number 1.19 dot dot dot, but that's equal to whatever the opposite number is divided by the adjacent number, right? So there's this number over number. Let's call this for E, I guess, radius J, just for it's all. So I won't bother doing it. Hopefully, not message me. I'll help you out. So process. There's going to be two processes to watch for when you're solving for sides. Okay, one easier one and a harder one. So the main process is always the same. You'll start is label your sides so you can figure out what ratio is involved or relates to the sides of the question, right? So in this case, you're looking for side X, which is, hey, on the opposite side here, that angle 50. If you're given the angle, you're going to be using it pretty much. If you're asking for the angle, it's more or less this. And if we're given that angle, opposite to it's the X and adjacent to it here. This one's opposite, right? So this is an opposite and adjacent situation. Where we have the adjacent, we're asking for the opposite, we've got the associated angle. So if you look at socket Philip, yeah, an opposite and adjacent situation, we have both of those ones, and so it's a tan situation. So we're going to say, okay, tan of the 50 must equal obviously the opposite over the adjacent. So I have to write that out every time, but tan of 50 will equal the opposite, which is the X, over the adjacent, which is and the tan of 50, we can just do on a calculator, 1.19. Seems familiar. Yeah, and so we'll multiply by 3 on both sides to get rid of that divide by 3. And we end up with X equal to the 3 times that 1.19. I calculated all the decimals. The calculator gave me a 3.575. If you use 1.19 times 3 rounded, it would be 3.57. Okay, so again, tan of 50, if I kept a bunch of decimals and multiplied by 3, I would have 3.57526 dot dot dot. Notice that that would actually possibly round that up to 3.58, right? Based on that. So don't worry about slight rounding errors like that. It's just if you kept the numbers and rounded. And so we selected, we noticed we have opposite adjacent sides that we're either we know or we're working with as we're looking for them. Looking for the X and we know the 3. So tan ratio is the 1. The next one, of course, here, let's keep going. You can press pause if you need to. It's the beauty of an online video lesson, I suppose. This is your opposite side to that 72 corner, and the other side here is your hypotenuse. So again, socket go up, streamline things here. That's that thing. And we've got, in this case, we've got opposite and hypotenuse. So I guess if you underline the O and the A for each, in all of the O's and A's, then you'll find there's 2 underlined in the tan area. In this case, the O and the H, there's only, it's only underlined both of them in the sign, right? So sine of 72 degrees will equal the opposite of the hypotenuse. So it's going to be the 20 over the y. Okay, so the first case you saw here, the number you're looking for is in the top. Okay, so this one, the number was in the top. And so, it's basically just a straight evaluate kind of situation. So you just solve, I guess it's still solving because you're multiplying by 3 on both sides, but it's simpler solving. When this one, the number's in the bottom, right? Numbers in the bottom, that makes the solving process a little trickier. And I'll show you how to do that. Right, so let's do sine of 72. Gives us 0.5 or so. Keep more decimals or use the 0.95. It doesn't matter. That's semantics at that point. So what we need to do for solving this, I'll show you the way most people prefer in terms of like, how it looks the nicest to do is you're multiplying both sides by y, right? That gets rid of the y from there. And then you see with this other line here where we have a times 0.95 equals a 20. So y times a 0.95 equals a 20, or some people might have written that as 0.95y, just sounds nicer. Not necessary though, and you divide by 0.95 because you're undoing that multiplication that's happening in there. Dividing. So I'm going to do 20 divided by 0.95. I use the rounded version. And that's giving me an answer left over here of y only because that stuff's gone. And 21.1 or so. It's actually 21.05. You know, so this is another answer where you might get a slightly different rounded version if you count more decimals. Okay, so it's 21, 21.1. Doesn't really matter. Okay, it's basically just you would decide how many decimals to keep based on how accurately you knew the original information and how many decimals you kept along the way. All right, so that's the tan and a sine so far. So let's keep going here. We have 44 degrees, we have an opposite side, and we have, of course, the hypotenuse across from the 90, the longest side. And so we have, in this case, SOHCAHTOA. It's just that sucker over here. And so we're looking at opposite and hypotenuse. Let's change that up because I meant for it to be the other type when I was making this. So let's make this be the side we're looking for. I'll modify the file for next time. I just deliberately wanted to have each type shown, right? So we're looking at the adjacent side here. So we're looking at adjacent to hypotenuse. So the two are in cosine. So cosine of 44 equals adjacent z over the 10. Notice that this is just one of those easy solving cases where you're solving for the number at the top. So I can just do cos of 44, 0.719 dot 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 whatever. Z over 10. And multiply by 10 on both sides. Z equals times 10, so it's just moving the decimal one spot, so 7.19. So how many decimals you get? Okay, so there's a sine that goes to tan. Two of these process, one of the little trickier process for solving. Good to go. Okay. Those. Now this is just an application question to show you how this could be used. So if you know you had 350 feet of string on a spool line for a kite, and you know it's at 30 degrees or whatever degree it's at, maybe 30 degrees is kind of low, but it was a really windy day. So if you look at that triangle that you could formulate, if you're looking straight up to the kite, that's a 90 degree. So that means that the Pythagorean theorem and sine cos of tan can be used. If it's not a 90 degree, you can't use them. We'll look at other processes since those tools wouldn't work, right? But this is a 90 degree triangle. And so we can identify the sides. We have our opposite side, have our hypotenuse. And so we look at SOHCAHTOA here. This time SOHCAHTOA. The more times you write that thing out, actually, the better, the more obvious, familiar to you. So opposite hypotenuse. So opposite hypotenuse, opposite sine. What we're used. Sine of 30 degrees equals the opposite over the hypotenuse. And it's totally okay to jump right to the numbers there. I'm going to communicate well here, point out, hey, we've got the hypotenuse. So I was going to communicate well, maybe I'll make it so you can read it. Hypotenuse and opposite over hypotenuse. Sorry, that's what's wrong. Opposite over hypotenuse. All right, so sine of 30 happens to be a half, but you can check yourself and see. So 0.5, it's a common one that comes up a lot. You start to remember after a while once you've done enough of it. And so we multiply both sides by 350. End up with the 350 divided by 2 gives you 175. So end up with a 175 here. And that was like feet of string out on the line, right? So you're saying like, therefore the kite is, 175 feet up. application question, it should do a therefore statement like this. Whereas in the previous question saying therefore x equals 3.57 doesn't add any value at all. So if anything, you can circle the result like I did on that one, circle, just draw attention to it. So that therefore statements are needed. All right, so that is sine, cos, and tan review. There's a assignment page for you to practice and submit. Okay, let me know if you have any questions. Message me on Teams or Detour. Have a good rest of your day.